Try not to keep you guys from the bar too long. All right, I'm Max Sobell. I work at Intrepidus Group, which is an NCC Group company now. I'm a senior consultant and the research co-director. We're based out of New York City. I've done some past research in NFC and mobile wallets. Big Bay Area sports fan, so it's good to see more Giants fans out here than in New York. Not doing so hot now, though. So this talk's going to focus on the Android open source project and OEMs and kind of where the two meet. What the OEMs add on top of the Android open source project, and then what the consequences are. So we'll look at rooting, some application issues. We'll kind of delve into some OEM-specific vulnerabilities that cover chipsets, backdoors. Look at the preloaded applications, show you guys a tool for that that I put together, and kind of give you an overview of rooting post-Android 4.0. That's the theme of this talk. First, what is the Android open source project? It's Android, right? What it really is comprised of is a kernel, hardware abstraction layer, some system services. Then it's up to the OEM, the equipment manufacturer, to implement the hardware abstraction layer code and drivers for the specific hardware. So like on this device, you can't just build the Android open source project, load it onto the device and boot it because you need the drivers, et cetera. Android open source project can be built as kind of pure Android for the Nexus 4, 7, 10, some Galaxy Nexus devices. But everything else has to add on there. And then what they'll typically do is add apps on top of that. So you get kind of a sandwich, an OEM sandwich at the low layer and then the application layer. So we're going to focus on the OEM components and not the AOSP itself. Some device components, and actually I'm really happy that, that Deviant gave his talk before mine because it covered a lot of the stuff that I was going to kind of try to rush through. So hopefully you're here for that. That was an awesome talk and gave a lot of good background for this talk. So the bootloader, like he mentioned also, it ensures that only signed code can be booted. It's the first thing that runs when you turn your device on. We'll cover developer unlocking versus exploit unlocking your bootloader, which will allow you to run unsigned code. So that's where a lot of the Android 4.0 roots are coming from. And I say 4.0, but I'm talking about 4.0, 4.1, 4.2, 4.22. The recovery partition, he covered how useful it can be, right? It allows you to mount and write to the file system as the root user before the device boots. It's kind of a separate partition you can boot into. Then we'll cover the file system and some permissions. So /system has your binaries. It's a read-only partition. We'll look at data local prop. We'll use that for an exploit. But that's settings on the device. And there you can set it to be a debug device and give you root access. And we'll look at an interesting symlink attack. So to begin, we'll start with bootloader unlocking. So like we said, it allows booting unsigned code, which could be a custom ROM or a kernel, once it's unlocked. So different OEMs have different ways of signifying that the bootloader is unlocked. HTC has an S flag, and they display S on or S off. Nexus has, if you've booted a Nexus tablet that's unlocked, it's got a little unlock symbol when it boots. Otherwise, it's got a lock symbol. And then Qualcomm chipsets have a secure boot flag. So keep in mind as we go through this, there's two very different scenarios for bootloader unlocking. There's developer unlock, where your data partition, all your text messages and app data and everything is wiped. And then there's exploit unlocking a bootloader where that stuff is not wiped. This is what the bootloader looks like locked. On the left there is an HTC device, and on the right is a Samsung device. So you can see, maybe it's a little small. Samsung official, do a little pointer. Does this point? Cool. Yeah, right up here. Samsung official, system official. And then here you can see S on and locked. So there's two locked bootloaders. So some of the bootloader exploit unlocks that have come out How many of you are familiar with at least one of these? Yeah? Okay, cool. Unrevoked was the first one. It was for HTC only, and they've kept it going. It'll unlock most of the HTC devices, set that S flag to off, and give you capability to leave it off. Moto Chopper is pretty recent. This is like a really powerful one. It affects a ton of devices. It was found by Dan Rosenberg, and then Odin, whoops, come back. I don't know if I hit something or why it's, anyway, you can still see it. Odin and Heimdall are Samsung. Heimdall is the open source implementation of Odin. It allows you to flash custom bootloaders. And it depends device to device whether that's going to wipe your data partition. Right, the sandbox is why that's happening. So then developer unlocking. Well, I'll just keep talking. HTC Dev, the HTC developer site allows you to use fastboot, which Deviant mentioned, and a device token to unlock the bootloader and wipe your data partition. And Motorola is now doing the same thing. So that's all right. Whoop. Yeah, we'll just get through it so you guys can go to the bar. You can suffer through that for free drinks, right? All right, so here are some unlocked bootloaders. So it is the same two or similar products. On the left there you can see unlocked, whoop, right above the fuzzy stuff, and then over here, custom, right? So this is what the bootloader looks like when it's unlocked. And then a developer unlock. So this was on my Nexus 7 device. Really simple. Fastboot OEM unlock. That's the whole thing. Then the bootloader is unlocked. And you can see there it says erasing user data. So this is a developer unlock. Wipes your user data, shows that lock state unlocked, and then that's really easy to relock. So on developer devices, the Nexus devices, really easy to lock and unlock your bootloader. Every time you unlock it, because it's not happening with an exploit, it's going to wipe your data partition, which can kind of be a pain. All right. So once you've unlocked your bootloader, right, we've covered the ways you can do that. You still don't have root access, which is what you're going for in the first place. So the bootloader unlock allows you to write or load the unsigned code, and then the next step is usually to flash a recovery image. So you can do that through fastboot, or to flash a custom ROM or kernel. So custom recovery images, I won't go into this too much because Deviant covered it so well. Clockwork Mod, Team Win Recovery Project, there's a million of them out there. And they're device specific. So the purpose of this is to allow you to write your SU binary, the root component, as the root user. Allows low-level system access for device imaging. It's really, really useful. Like you showed how you can back up your whole device, image it, do whatever you want, and then flash it back. Okay. Finally, root. So all root is just like Linux root. It's a binary with a set UID bit owned by root. So when you execute it, it gives you a root shell. It's typically just named SU. It's in system xbin SU. The other type of root that you can have is debugging root. So there's no binary here. If you have in data local prop any of the following here, just keep these in mind. When you start up ADB, you'll have a root shell. So two different kinds of root that you can achieve. If we wanted to hide root, for example, most applications, probably 95% of the applications I've ever looked at, are only looking for evidence of root, right? They're looking for superuser APK, system mounted as read-write, some exploit junk in data local temp, or that SU binary. So one really simple thing that I like to do on devices, once I root them, to kind of hide the root access from malware or from applications that are detecting root is just name it blah. Name it whatever you want. Just keep it in the system xbin directory. And you just run blah then, right? Instead of su, you just run blah. You have your root shell. Same exact thing. All right. How are we going to root these devices? So we'll divide it up into 3 kinds, right? There's drive-by roots. So these are the bad ones. These are the ones that an attacker might use once they get physical access to your device. Or some of them could be run from malware. Like we'll look at the ingenious attack, which could be run from malware. Then there's the user-initiated roots that require the user to have physical access to the device, probably interact with it during the attack or the exploit. They may be difficult to execute, have a race condition or something. And then there's the data wiping roots that we covered, and they're not particularly interesting. So drive-by device roots, just to start with. On a lost or stolen device, an attacker could execute these to gain access to your data. So these are the really bad ones. These are the ones that we'd like to prevent. If my phone gets lost and it's locked with a passcode, I don't want someone to have access to that data. If one of these roots exists on the device, if the device is vulnerable to one of these drive-by roots, an attacker could have access to my data. So these could be bootloader unlocks. Obviously, if you have ADB enabled on your device, it opens up a lot more attacks, right? So that's something that you can do to prevent some of these from becoming drive-by roots, is have ADB disabled. So then we have the user-initiated roots. Can't be initiated by malware. The user is probably aware that his or her device is rooted. Some are complex, and then some are simple. So we'll root one of the devices on stage here using one of these user roots. Data wiping roots, we covered these. All right. So what we've seen in Android 4.0, as opposed to Android 2.x and to some extent 3.x, is they're much different rooting landscapes. Android 4.0 added a lot of protections. On-device encryption, ASLR, DEP. I'm not an expert in these. I just know it makes it hard to exploit the device. Much, much harder to write local exploits. So we used to see a ton, right? How many of you are familiar with these? Zergrush, Gingerbreak, Rage Against the Cage. There's a million of them, right? I couldn't even fit them all on one slide. These were all the local privilege escalation attacks on Android 2.x. Most of these could be drive-by roots. It was really kind of like a Wild West landscape. Post 4.0, I've seen one Android open source exploit, and it was really involved race condition with the backup utility. And I think I saw this used to launch a developer unlock to change your carrier ID code, allow you to launch a data wiping attack. So pre 4.0 and post 4.0, the landscape has changed quite a bit. But devices come out, and 2 days later, they're rooted, sometimes 2 hours later. So how is that happening? So most of it is focusing on OEM components, the kind of OEM sandwich, either the applications or the low-level code that we talked about before. So we'll cover Exynos, Moto Chopper, and then some OEM-specific backdoors. One of the main ones was the ZTE hard-coded password, which made the news. People were kind of up in arms about this one. LG has a similar backdoor. It's not a remote backdoor, but it's less public. So I've got an LG device here, and we'll try to root it. We won't tempt the demo gods too much, but and then we've got a ZTE device with FTM mode. Again, these are all public. I'm not like dropping 0 days. We'll walk through them here. So Exynos briefly, it's a Exynos chipset is an ARM-based system on a chip manufactured by Samsung, which means Samsung is responsible for the driver component to interact with the hardware abstraction layer, right? They're adding that code on top of the Android open source project. So the issue, at the very bottom, you can see here, the second command that I issue is just lists out the Exynos memory dev, and it's read-write for everybody. And the mistake that Samsung made is that that gave you read-write access to all physical memory. So there, it's pretty simple to find a memory location that you want to write to it, and get root. The Exynos abuse APK made by this XDA member, AnalFest, kind of patches the issue, changes the permissions once you have root to the top here. Probably should have reversed these, so that other applications can't exploit it. But the real patch had to come from a kernel patch from Samsung. The other interesting one that affected a ton of devices, I should mention that Exynos was Samsung only, and it affected most of the line, all the devices with these Exynos processors. Moto Chopper also affected a ton of devices. It was called Moto Chopper, I assume, for Motorola, but it turns out it affects Samsung, Motorola, Huawei. This device here I rooted using Moto Chopper. So Dan Rosenberg from Azimuth does tons of awesome Android security research. He found an ARM trust zone exploit to unlock the bootloader, and then give you a root binary. It's really simple. It doesn't take a few minutes. It takes like a second. And then you reboot the device and you have root. So this is potentially something that a malicious application could run on the device and then just wait for the user to reboot it, or send a reboot command once it has root. So anything with this Qualcomm chipset that relies on ARM trust zone is vulnerable to Moto Chopper. So again, this is not an Android open source project component. This is a Qualcomm component. A Qualcomm component. All right, so we'll tempt the demo gods and we'll try to root this LG device. But pretty briefly, someone posted this online and I was like, that can't be true. So I pulled off ADBD and threw it into IDA. I think the guy was Giant Prune. And he says, look at SD card G security. So I'm like, okay, so I look at it in strings. Just really briefly, it's not a remote backdoor. It doesn't mean that LG has access to your device. And it just gives you a root ADB shell. So I opened ADBD and IDA, went to the string cross-reference, and you can see here, it tries to read this file, SD card G security. And without being an assembly expert and reading all this assembly, you can see here, check LG official, enable root. So maybe that file has something to do with root. So, oh, this is going to be tricky to type from here. All right. Let's make sure we're not rooted. All right. So, I just touched that file, right? There's nothing in it. It's now just a old node on the disk. So now on the device itself, all I'm doing is, what am I doing? Developer options. Okay, I'm just going to unplug it, turn off USB debugging, wait a second, turn it back on. Yes, I want to turn it on. And I'm root. So that is super simple, and that's LG devices only. Oops. Let's see, back to here. Oh my God, I don't know how to use a Mac. All right. Okay, so this was my little backup slide. Yeah, you pretty much just follow the directions and you get root. So this kind of hidden root is not so bad, But like 2 days ago, once I had finished preparing for this talk, someone, JCase, released LG Pwn, which is a race condition in an LG-specific backup app. It's locally exploitable, and he says that in some cases it can be a drive-by root. It could be something that could be used by malware. So this one is much worse, right? It affects 40 plus LG devices. So between this Moto Chopper and Exynos, you've probably got 90% of the smartphones out there covered, right? 90% of the popular devices. All right, this one will really tempt the demo gods on. So I've got this ZTE device. I'm just going to cover a soft linking vulnerability. So this was a really common one. Maybe 6 months ago, we were seeing tons of devices being reverse engineered, and then the initialization scripts kind of exploited through symlinks. So when the device boots, the initialization script will go through and set permissions on particular folders. So one folder is data local temp, /data /local/temp, and you have full write access into that folder. So it wants to give you write access when it boots. So we'll try to exploit that. So the first part of this root, the device is off. I'm just going to boot it into FTM mode, which is their engineering mode. So picture I steal the device or you lose it. I turn it off, and then I turn it on, volume down and power, and it'll just take it a minute. So the way that it should work is you should not have write or execute access in data local. The way that it works in FTM mode, however, okay, now you can see it just says FTM, just like on this slide. Okay. So, all right. So you can see you should not have access to data local. You do in FTM mode, and it'll allow you to symlink that. So from here, it's pretty simple. Oops, let's actually get out of here. I don't like typing in the shell. So we're just going to link data with data local temp, and actually. I'm just going to make a backup of my data local temp. Okay, cool. So now we're going to link data with data local temp so that when that initialization script goes, we're going to get write access to /data. And what is located in /data that we looked at before? It's that local.prop file, which controls whether the device is rooted or not, right? All right, so let's reboot the device now. And it'll just take it a minute, and we're going to reboot into standard Android. We're not doing the FTM stuff anymore. So there's two issues here. The first is that the init script doesn't check if it's a symlink before it sets read-write execute permissions on data local temp. And then the second issue is FTM mode. This can pretty much undermine any security that you set on the device. And this is a custom OEM component on top of the Android open source project, right? So let's see, we have our device back. Okay. So now we'll just echo this ro kernel qemu to data local.prop. Okay. And now we'll just show data. Whoops. Yeah. So we didn't have it before, but now we have read-write access to /data, and you can see the contents of local.prop. Whoops. We did do that, right? Did I miss something? Cat load. Oh, thanks. Okay, so it's fine. All right. All right, we'll reboot it. And it'll take it a minute. And then that local.prop file will get read when the device boots. And we should have root. Thanks. This device boots particularly slowly. All right. There we go. Another root. Thanks, guys. Okay, so I'm going to get this one kicked off before I talk about it. Oh, go away. Because it takes it a little while. What I'm going to do is use a tool that I'll describe in a little bit to audit this Huawei device and to show some entry points into some of the default applications. So you'll just have to trust me that I will explain it, but I'm going to kick it off now so it can go pull off the apps and decompile them while we're talking about the rest of the stuff, so I don't keep you from the bar any longer. So this is the tool. We're going to get the APKs. We're going to filter. We want all the ones that are OEM-specific called Huawei. Okay. So it's going through. It's going to get them, and it's going to decompile them. And we'll talk about other stuff. Okay. So beyond root. We covered some ways to root devices using OEM components. Now we're going to cover some of the default applications that are installed by OEMs. So we covered the bottom layer of the OEM sandwich. We'll look at the top layer now. I'll give you a little bit of background on Android applications. How many people are Android developers or know everything that it says on this slide? Okay, we're going to go over the whole thing. So pretty much these default applications turn your sleek little Android man into Jabba the Hutt, right? He's bloated and he's got all the applications in him. So applications have endpoints to communicate with each other, and sometimes for inter-process communication, right? An app wants to launch another part of an app, so it'll use these endpoints. And these are declared in a file called android-manifest.xml, which is packaged with every Android application. Android applications are a .apk file. So that's what the tool is doing in the background. It's pulling off the ones with Huawei in their class name, and it's going to decompile them. So we're going to look at 4. Content providers, activities, services, and receivers. And they all have distinct functionality. We'll cover how to attack each one. We'll look at permission leakage. How many of you have heard of permission leakage or have seen it in the news? Okay, it was kind of a big deal, I guess 6 months or a year ago, when people started discovering that these applications that are installed on your device have permissions that you never granted to them because they came pre-installed and you can't uninstall them. And they could potentially have unprotected endpoints that attackers could exploit. It's kind of the high-level overview of this. And then we'll look at shared UIDs and how some of the default applications share UIDs kind of undermine the Android security model. So activities, services, and receivers are activated via these things called intent messages, which is just the Android OS messaging system. They get passed from app to app, and they launch various components. These 3 endpoints are launched via intent messages. They can be sent from app to app, or they can be sent via ADB. So that's what this tool is going to do, is spit out a way for you to interact with each one of these endpoints using the Android Activity Manager, AM. So this is what it looks like. An intent filter declared in Android manifest that we talked about before. This one's for flashlight test. You can see the activity. And activity is just like a screen, and then the intent filter. So if an intent down there, ADB shell, AM, activity manager start, give it the right component names, it will hit this code. So that you can then decompile the application and look and see the actual code that it's hitting. So content providers are different kind of than the other three. They're a handle into a database. You can access them via content, // they specify an authority for access, and then you can access a table after the authority. Activities make up an application's UI. When you say you open up your email, that's one activity. Then you click an email message, it opens up a new activity. And you reply, and it opens up a new activity. Every time you hit back, it closes one activity. Activities can be declared in the Android manifest, and they can have intent filters as, am I doing that? And they can have intent filters as child objects, and they can be launched via intent messages. Services are processes that run detached from the main thread. Their point is not to block the main Android thread. They can also contain intent filters and can be launched that way from the command line or from another application. And then receivers are pretty interesting. They can also contain intent filters. So those last three that we covered before can all be launched via intent messages. All right, so you have some general protections for these Android endpoints. You can have a permission on your Android manifest, which specifies who's allowed to interact with that application. You can create permissions, and then you can specify a protection level. So if you say dangerous, if an app requests your permission, the user gets a little notification that that app is requesting a dangerous permission. Or you can say signature or system, which is always what we would recommend. So that allows only applications in system app or with a shared signature. So if I create two apps and I create a permission that says protection level, signature, or system, my apps can talk to each other, but nobody else can talk to them. You can also set all your activities and services and receivers to be exported equals false, which means your application can access them. So one portion of the application can access another portion, but nobody else can access them because they're not exported. So post 4.2, it's a little bit different story. Pre 4.2, this was a big issue because if you have an activity with an intent filter, under it, it's automatically exported. Everything's exported false by default. If you have an intent filter, it gets exported. So I think people didn't totally realize that. So post 4.2, it's always false unless you explicitly say exported equals true. Content providers. Here you can specify a little bit more granularity. You can specify read and write as two separate permissions. So people can read the database, and then if you have another permission, you can write to the database. And you can also say exported equals false for these. And then activities, same story. You can set a permission on it. You can set exported equals false. Services, same thing. Receivers, a little bit different. Any app can register a broadcast receiver, and then it's up to whoever sends that broadcast message to specify the permission required from the receiver. So the permission that the receiver needs to have in order to access that broadcast message. And then again, you can set export equals false on the receivers. Okay. So there's a major problem with the preloaded applications, and there's two layers of these preloaded applications. You have the applications that the OEM is loading, and you have the applications that the MNO is loading. So by the time your Android device actually gets to you, if it's not one of the Nexus devices or is running pure Android, it looks like Jabba the Hutt, right? It has 2 layers of pre-installed apps. And then they're installed with default permissions that the user never went through and accepted. So permission leakage, we'll cover like a made-up example and then a real-world example. So say you have a weather application and it requests location permission. It's pre-installed on the device, it's granted location permissions, and then it exports a content provider and an activity. Well, because it has no permissions on the content provider and the activity, it has the potential to be exploited or to leak location data, right? You can see that path. It can get location data, and then it exports sections of its code to be interacted with by other applications. So potential for data leakage there. October last year, Thomas Cannon released Android SMS spoofer. So this is real-world permission leakage. And it was actually on an Android open source project application. So it exported this SMS receiver service with no permissions restrictions. So any app could send an intent message to that receiver, and it looked just like you were receiving an SMS message. So that was kind of a social engineering thing. You could get the user to act on a fake SMS message that they had received. All right, so I put together a tool to kind of expose these endpoints and to look at Android endpoints with no permissions and no protections. And I made the mistake of letting my coworkers name the tool. So they named it the Manifest Analyzer, AnalFest. So it parses Android manifest files into objects. Like you saw, they're XML files, and if the top level tag has a permission, all the XML children should inherit that permission. So it's an object-based parser. And it's the point of it is to kind of give you a quick way to assess OEM applications on a device and access various unprotected components and then kind of give you a place to delve deeper. So hopefully this thing ran in the background. Cool. Look at that. So you saw the command that I issued. It was just this. So it launches AnalFest, tells it to get anything with Huawei in the title. It goes through, and it finds, let's see if we can make this bigger. It finds all of the unprotected activities, and on this device, it's a ton. It's not usually this many. And all the hidden codes, so the pound codes. You guys remember the Samsung vulnerability that would allow you to wipe someone's device. So it finds stuff like that. So it'll go through each manifest by manifest, and then it'll give you a summary at the end. So there are no unprotected content providers. There's lots of hidden codes, and then lots of hidden menus. So where was that one? The flashlight one is kind of cool. So then we can just pop this in the other window because the device is still connected. Launch this activity. And it pops up a screen and it says flashlight test. So there we go. We can turn on the flashlight. So there's more malicious ways to use this. You can sometimes find kind of engineering menus. A lot of interesting hidden menus are exported as activities. Okay. It looks for debuggable applications. And then it shows all the applications which share a UID, which right now it's just looking for applications which request sharing the Android system UID. So I'm really not sure why some of these need the system UID, which undermines the Android security model a little bit, because any application with the same UID can access data from other applications with the same UID. and it gets the same permissions. So if you were to exploit one of these applications, you'd have the permissions of the system UID. So it kind of adds an unnecessary attack vector. All right. So we'll look at some of the things that this tool found. Yep. We'll start with content providers. So I ran it on this LG device, and it found this unprotected LG email content provider. So in the manifest, it looks like this. You can see Android exported equals true, and then you can access the content provider from there. Services, which are not particularly interesting, except here. This is again on this Huawei device, and I think one of the ones that came up before there. It's a copy file service. So you could then launch that service from the command line. You could maybe fuzz it or add in some extra strings. You can reverse the application and figure out what it's doing with the extra strings that it takes in. Unprotected activities. So we saw the flashlight one. Here's one for listing files, local file list activity. So this one I decided to decompile the application, look at it in index.jar, and you can see actually where it receives the intent message, and it looks for an extra string called path, and then it passes that off. So you can see if we launch it with the same thing that AnalFest spit out, and then --es, which is just the extra string, and we say path, and give it a path, it starts up that intent message, is received by the application, then processed, and it gives us an activity which lists that portion of the file system. So as I was preparing for this, I saw that Quark's lab had given a talk that picked kind of solely on Samsung. And they found a great example of an unprotected receiver. So I asked them, and with their permission, I'm showing their example because it's so cool. So they did the same thing. This is like me recreating it. They found a place in the application where the input is controlled by an intent message, and it says, do shell command, and launches a shell with a param string. So if you launch that and you just give it an escape, you can run any shell command that you want by launching an intent message. So this is something that malware could do, something you can do from the command line. And you can see here we launched the intent, and then I just cat that file, and you can see it just ran ID and put the output into that file. So this could be used to download malicious files, to launch an exploit, to do really anything. So in summary, we saw the LG backup program. We've looked at some app stores and have some vulnerability or bug reports pending that I can't talk about yet. Don't reinvent the wheel. Annoyed Picard says, why would you do that? Use the Google Play App Store. Use Android's Wi-Fi hotspot. Don't implement a Wi-Fi connection manager or backup programs. Keep the apps that are loaded on the device to a minimum. So, example App Store issues. If you have a third-party application store as one of the default apps on the device, you can't run it securely because of how Android is set up. You have to either check this box that lets unknown sources, lets you install applications that your operating system doesn't recognize the signature for. So that could be something that you've signed or someone else has signed. I think that's how the Amazon App Store works. Or you have to do this workaround and have Android Intent Extra, not unknown source. So what that says is, if you include it with the intent messages, don't treat this application install request as if it were coming from an unknown source. Treat it as if it were coming from this application that launched the intent. So if that's an app store, the operating system trusts the app store. By extension, the operating system trusts anything that the app store wants to install. that combines with you need SSL TLS for your app store in transit. Otherwise, that application could be modified on the way. Who knows what could be added to it, and then it would be trusted by default and installed. Because you're bypassing the signature checking, lots of bad things could happen. We saw that long list of applications with shared UIDs, the shared system UIDs. System UIDs are under 1,000, and no applications should use these system UIDs because they should be requesting individual permissions at install time. So AnalFest I added in UID checking. Like I mentioned before, OEM applications that have a shared system UID kind of undermine the security model. It allows access to the existing permissions for that user or that user ID, shares data, and it gives you the same UID as an existing process and kind of muddles the sandbox. Okay, to the bar. The wrap up. The Android open source project can really add whatever it wants, whatever exploit preventions, whatever encryption or security, but until OEMs start paying attention to security on the applications that they're loading onto the device and the drivers that they're writing for a device, devices will continue to be rooted within hours of coming out, and you'll see exploits which affect entire classes of devices. So what the OEMs can do, well, of course, it's not possible to not modify the Android open source project. Everyone needs their special brand of Android running on the device. One thing you can do is patch vulnerabilities and then deploy the patches quickly. Bundle as few applications as possible. I don't need Roller Coaster Tycoon on my phone in a place where I can't uninstall it. Don't reinvent the wheel. And then don't share user ID, system IDs unless it's absolutely necessary. There's no reason to kind of work around the sandbox. And then this would be like a dream come true. Don't put pre-installed applications in a read-only file system so the user can't uninstall them without rooting the device. Put them in data app where all the other happy applications go that can be uninstalled by the user. And last, use a locked bootloader. Don't allow an attacker to run unsigned code on my device. What the mobile network operators are kind of the man in the middle here. What they can do, they can vet the applications that are preloaded. They can ask the OEMs not to preload applications. They can help the OEMs push out patches quickly once those vulnerabilities are discovered. And they can mandate the latest software versions, the latest Android, the latest fixes on whatever applications the OEM has. And they cannot reinvent the wheel. We saw, okay, what you can do. So actually, Deviant's talk was a perfect overview of this slide. Kind of his whole talk was this slide, right? And he went really into great detail on it. You can install Cyanogen mod. Barring that, you can keep your device up to date when those annoying pop-ups come up that say, we're going to need an hour of your device, and then we're going to reboot it at the end, and you could lose some data. You have to do it. Be careful in downloading from marketplaces, and use Google Play, which is using signature checking and not trying to work around it. Don't root your device, and if you have to, root it and then hide root, like we went over before. Don't disable bootloader code signature checks. They're there for a reason. And check permissions when you're installing applications and check them on the pre-installed applications. So what we'd like to see in Android 4.3 is a Google-controlled secure boot chain, kind of like the Windows 8 model. Native support for more hardware, so you can just build the Android open source project and deploy it without room for OEM mistakes writing drivers. And then the ability to revoke application permissions, which Deviant covered. If we could granularly revoke application permissions or spoof the information that they're getting back, like GPS, that would be a dream come true. So I posted my tool here. I will continue making updates to it probably over the next month. You can grab it now. If anyone wants to contribute to the repository or shoot me an email with features you'd like to see, the end goal is to have kind of an API that anyone can just import as a Python library and then use it to parse through your manifest file. This is my Twitter. I don't tweet very much, but feel free to tweet at me. And IG is hiring. So thanks a lot for listening. Enjoy the open bar. I think we're a little bit early.
Yes.
Check them on the pre-installed applications. So what we'd like to see in Android 4.3 is a Google-controlled secure boot chain, kind of like the Windows 8 model. Native support for more hardware, so you can just build the Android open source project and deploy it without room for OEM mistakes writing drivers. And then the ability to revoke application permissions, which Deviant covered. If we could granularly revoke application permissions or spoof the information that they're getting back, like GPS, that would be a dream come true. So I posted my tool here. I will continue making updates to it probably over the next month. You can grab it now. If anyone wants to contribute to the repository or shoot me an email with features you'd like to see, the end goal is to have kind of an API that anyone can just import as a Python library and then use it to parse through your manifest file. This is my Twitter. I don't tweet very much, but feel free to tweet at me. And IG is hiring. So thanks a lot for listening. Enjoy the open bar. I think we're a little bit early.
Yes.